This information is brought to you by Charles Sturt University.
Hi, welcome to another video on how to calculate the flux. This is a different one just to where the surface is a bit different. So the question is, we have a vector field, this one happens to correspond to the force due to an electric particle. So we've got an electric particle at the origin. This is what the force is for another electric particle of the same charge. So basically the idea is the force is I pushing away from the origin. So it's always pushing away, and that's divided by the length of it cubed. So the force diminishes in strength the further away you get from the particle. So if you've got two positive particles next to each other, the force is pretty strong diminishment, but as they get further and further apart, the force drops down dramatically. So that's the force field, and what we're doing is we're considering a sphere. So trying to give a little 3D look about it. So we've got a sort of a sphere sitting centered around that with this electric particle in the middle. How much of this electric field flows through the surface is the idea. Is what we're trying to work out. So we're trying to find the flux. So the integral of f dot dA or ds, to emphasize the surface area in this case, of this particular case. So the way we're going to try to do it at first glance is, because the surface is a sphere, we can at least work out what the normal is at any point in time. And so if we can work out the normal, that's good. And so we can use this sort of formula. So if the normal is easy to work out, then at least this one's doable. And then we'll have to try to tackle a surface area integral in a second. So if you sort of think about it, so with the sphere, so if you pick this point here, then the normal is pretty much pointing perpendicular out from the surface. So if you draw an arrow from the origin, it's in the same direction. So it's actually pointing in the same direction as it is to the point itself. So the normal really is in the same direction as the vector which goes from the point, from the origin up to the point. And this vector here is r. So it's in exactly the same direction as r. But little n, is always referring to a unit normal. So we need to make it in the same direction, but divided by its length, essentially. Now, just recall that r, it really is the vector, and I can write it down as a x plus yj plus zk, or you're writing in terms of just the coordinates, so it's just x, y, z. So r is just another way of saying just the normal x, y, z coordinates. And so the length of r is the square root of x squared plus y squared plus z squared. And it's convenient to call it, say, little r without little tilde underneath it. So I write r tilde to indicate the vector, and r is just a scalar, which should be the length of it. Now, in this particular case, all the different points we're going to consider the normal on in this is basically sitting on the sphere of radius r. So this little r, which is sort of my general function, happens to equal r on the surface. And so the normal is this vector r divided by the actual radius of the sphere at any point in time. So putting it together, we therefore have the double integral, so over the whole surface area of my vector field, r on the length of r cubed, so we'll call it little r cubed, it's a scalar, dot producted with r over the radius of the sphere, and we're integrating over the whole surface area. So ds with no tilde on it means integrating over the whole surface area. So r dot r is the dot product of the two, which is going to give you the length squared. That's going to give you r squared. We got an r cubed. We got an r integrating respect to ds. So lots of things cancel out. So you got all the r squared cancelled out with two of the cubes, just leaving one r on the bottom. And then the other thing is on the surface itself, little r is just equal to capital R, which is a fixed radius. So little r is a variable, so it really does depend upon where the position it is. Capital R is fixed, that's a fixed radius. And so since capital R is fixed, I can factorise it out of the integral. And therefore, we've got 1 on r squared times by the integral over the whole surface area. So that's going to be, if you integrate over the whole, if you integrate a little bit of surface area of the whole region, that's just going to give you the surface area of a sphere. And if you can't remember what that is, the surface area of a sphere is 4 pi, the radius squared. And you can see these r squareds cancel out, and you're just left with 4 pi. And so therefore we've worked out the total flux of this particular vector field, so something like Coulomb's law. When you integrate over a sphere region, you get something like 4 pi. And so the normal version of Coulomb's law, which you may or may not have ever seen, often buries the 4 pi in the formula for the function to actually get the answer of something like 1 in the end, as a matter of fact. That's what you commonly see. And that sort of theorem is called Gauss's law. And that's something you might learn if you do a bit more electromagnetic in physics, which you may never ever do, but that's where some of this fits into this particular theorem. But that's basically in terms of the mathematics. The key idea is here is that any sort of flux integral can be thought of as being f dot, the normal, unit normal, integrating over a whole surface area. And again, that works nicely so long as the surface area is straightforward. And so in previous cases we've considered is a bit of a plane matching the coordinate axis, so you can just use simple double integral. In this case, the surface area was a known shape, namely a sphere. The next example I'll look at is where the surface is non-standard and how you approach that case, which is a bit different. So I hope that helps.